Again, back when I was a student, that was before there were really any pictures printed on computers. The computers were like a typewriter; they just made alphanumeric. But it was very famous that people would invent kind of like pixels. You know, the paper was this wide, and it had a certain number of columns on it, 132, the standard for most computer paper. So they would start, say, putting an X here, and then maybe a few X's, and then maybe add a few O's. And so people that were really clever could use a mix of different letters to create something that would sort of look like a picture. Right? That was always, everybody else would be very impressed. Wow, that's cool. But it was never a picture, right? It was just letters, you know, maybe some ones in there, a 9, I don't know. But it's whatever looks like an I, whatever looks like an air. So that was very famous. Okay, any questions about this?
I have a question about C.
Okay.
C++ is a kind of basic program to write another program. What will be another one to write C++?
Yeah, so what are some other compilers?
Yeah, to write C++.
Yeah, there's one called COBOL. Incidentally, COBOL was probably the first compiler. Right? We talked about compilers, right? The compile step. That's when you turn a higher level language into machine language. That's what a compiler is. COBOL, I believe, was the very first one. And somebody out there this morning signed up. I won't say who it was, but the inventor of COBOL was one of those names on the list. And it was a woman. She wrote the very first compiler. Yeah, by a woman. But there are ones called, there's something called BASIC, something called Pascal, of course Fortran. Maybe there are others too. But these are the main ones, I think, plus as well as C++. I think the language BASIC, I think that's the basis that C++ came from. All right, good. So let's go through. I'd like to go through the rest of the C++ lectures today, one after another. All right, all of chapter 2. And then if you need more time to absorb it, if it doesn't all make sense, you can work on homework assignments. We can talk about them in future days. But I hope by the end of the class today we're done with chapter 2. Are we ready over here? Buffalo's a cold climate, and I love to ski. So these are a couple of pictures from a ski vacation in Canada, close, not too far away. This will just take a minute. Oh, be back up for a second. Okay, so it's in a remote location in the mountains, so you can't get gas very close. Okay, that's my wife and me, and there's the resort. You can see there's a little bit of snow. So this is from up on the ski mountain. Everything down below is, these are clouds. So everything is underneath the clouds. You can see some really high mountains. That's a little garage outside. That's where they keep the tractor to clear the snow from so people can walk around. More high mountains. It's the picture from the ski lift. And you can see here's the ridge up here. The scale you can't really tell, but that's a person. Yeah, now this is with the telephoto lens. You can see them better. Yeah, that's my wife and I. Again, you can see we're very high. These are clouds down below us. So another mountain nearby. So, just pause for a second. I'll tell you, I thought this was funny. So, I was a student from Thailand one year, a PhD student, and he stayed with us and we took him skiing, and he took a lot of pictures around the area, and he sent them back to his parents. His parents had never seen snow, and his mother said, why did you take black and white pictures? Why didn't you use the colors on the camera? And he said, that is the color. So, you can see the clouds down below. This is one of the ski lifts that brings the people up the mountain. This is very extreme skiing. This is a cliff. There's no people on here, but a person would be about that tall. So this is very difficult. You have to be very, very good skier to try that. So, there's a couple right here. Let's look at that. 2.7. Okay, do you have this one? Has anybody looked at this one yet? Yeah, some have. Okay, so this is still the do while. Well, actually, do while is new. We did if, else. We did while. We did we do for? I think we did for. Yeah. So this is yet another kind of logic, do while. In fact, did we do this one? We did do this one. Maybe not. Okay. The assignment operator, the unary operator. Yeah. A plus equals B. Yeah. Okay. Okay, so the plus. Alright, so just to, here's the syntax, right? It's not in this form and it won't work no matter what, even if the logic is good. So you write a do, then you write everything that you want it to do, so this can have lots of statements in it. And then after that comes while. And then the while should be a logic, Boolean, a criteria check for the ending loop. So if this is true, it does this again. If this is true, it does it again. When this is false, it continues. Okay? So sum a series of numbers. We talked about doing the sine loop, right? I'm sorry, not a loop, but calculating the sine of x. I wrote it as a So you might want to decide how am I going to end the series? When should I say this is the end of the series? So the check, in that case, the criteria could be that the last term that you just calculated in the series is below some certain percentage of the overall. Right? So let's say you're calculating that the sine of y is equal to y minus y cubed over 3 factorial plus y5 over 5 factorial minus y7 over 7 factorial. Right? This is, in theory, that's an end of the series. In practice, though, even if the sine of y was a double precision, only 12 digits get stored. So your test could be, for this test right here, the logic maybe would be you calculate the next term in the series, divide that term by the sum, the sine of y, and if it comes out to be less than 0.00000001, 12 digits, there's no reason to keep calculating terms because it won't get stored anyway. Everybody understand? So this logic can be really good if you have a series that you want to calculate and you're not sure how many terms it will take in order for it to settle in on the final answer. That's not the example he's given. Right? The example he's given, he has a fixed number of terms. He's adding every number, each one bigger by 0.25 until he gets to 3. So this isn't the same example I'm talking about. This actually isn't so clever because you know how many terms. But something like this, you normally wouldn't know how many terms you should include. Right? And it'll be different depending on how big y is. If y is really small, the sine of y is approximately equal to y. Because already, if y is really small, already this term doesn't even really matter. This term definitely doesn't matter because of the power. For instance, if y is something like 0.001, 1/1000, this term is 1/1,000,000 because it's 1/1000 cubed of the size of that one. It's 1,000,000 times smaller than that one already. So there's really no reason that you would keep it. On the other hand, if y is big, if y is almost equal to 5/2, say 1.4, that's a big number, then that means this series might have to be calculated for a long time before it settles down. So how do you decide how many terms to keep? Again, you could put in here, your logic check could be when the percentage of the next term in the series is a small percentage of whatever the current total is. That's when you put it. Everybody understand? Did you have a big lunch today? Cup of coffee? Everybody sort of... So, give me a little feedback. Let me know if I explained it. Because if I didn't explain it, I want to make sure it's easy. Okay. All right, so let's go ahead and see what happens. It's going to calculate that series. So here's the do, and everything inside of the do will happen as long as this is true. So it goes through the first time. The starting value of y is 1, right? The starting value of x is 0, and then x gets added to x plus dx, right? dx is 0.2.5, and now is x less than x max, and the answer is yes. So it comes back up, and y gets added to x. Actually, let's say that backwards. X gets added to y, and then dx gets added to x. And then it checks it again, is it less than x max, and so on. It keeps going. And it's important to notice this is less than or equal to. Right? So what is the value of x when the loop is exited? Okay, it comes through the last time and it sets x equal to 3, right? Is 3 less than or equal to 3? Yes. So it goes back and it does it again. With now the value of x is 3. It gets to here and it adds 3.2. Now x is 3.25. That's when this fails. That's when this becomes false. So when it comes out of this loop, the value of x is actually 3.25. But the last one that gets added is 3. Because x gets added to y first, then we get a new value of x. If these two statements were backwards, then 3.25 would get added to y. Everybody understand the difference? Okay? Okay. So the value of x when the loop is exited is 3.25. But that's not the last value that actually gets added to the sum. The last value that gets added to the sum is only 3, because it changes to 3.25 before it exits. All right, so here's the output statements. And you can exit this, you can run this on your own. Okay, so for loop has a similar logic. For a statement 1 is the initial value for the loop variable. So I know I've already done this example in class. Statement 2 is an exit criteria, a Boolean statement. Statement 3 is increment the loop counting variable. And no semicolon after that. So this statement, and who knows why, whoever wrote C++, they set it up this way. This is a statement that you do not put the semicolon on. Okay. So after the after the for statement, you put the statements you want to execute. So if there's more than one statement, same pattern that we see in all these commands. You use the brackets if there's more than one. If there's only one statement, you can just put it in the same line. And then at the end of the statement, you would have a semicolon. Okay. Okay, for x from 0 until x is less than or equal to x max. And x gets changed each pass through by the value dx. Then inside of the statements, each time through x gets added to the value of y. Y starts at 0. So the first time through x will be 0, so it doesn't add anything. And it gets changed by this amount. Second time through it's 0.25, it gets added, and so on. And that lasts for as long as x is less than or equal to x max. So the last time through, the value of x is 3. Then it exits. Then it goes out after that. And you run it. Right? I think that you can look at that other example. Unless you want to back up and take a look. So this is a slightly different logic. So here, x0, x less than or equal to x max, and the value of x is changed every time through, and y is equal to x plus y each time, because it's only one statement. So if you remember, the previous code had curly brackets, and it had changes inside. This doesn't need it. So this does the exact same, this is just a different way of writing a statement that does the exact same thing we do. Are there any questions? Yes. So the for logic is like while, right? It's for this time period that this set of 3 statements is valid, then you should do this. When this is no longer valid, then don't do that anymore. Okay, so the logic is starting at x equal to 0 until x is as long as x is less than or equal to x max, which in this case is set to 3, is if those two are true, each time you go through, add dx to x and calculate this statement. Y is equal to x plus y. So because we start with y equal to 0, we add x to it. So the first time through, y would be 0.25, and the next time through, it gets 0.5 added, and so on. Okay? It's the exact same logic as the previous program. But why don't we back up for a minute now? We're back up to the last slide. See, in this one, this statement is exactly the same, but here he wrote brackets. And he also wrote this a little bit different. Y plus equals x, this unary statement. So this statement, y plus equals x, that's the same as y is equal to y plus x. And also, just a second, let me just say one more thing. Here he put brackets, so you could have multiple statements inside the brackets, but he only has one anyway. So because it's only one, you might as well just put it on there and forget about the brackets. So that's what's on the next page.
What is the advantage of for loop and do loop?
Yeah, in my opinion, it's a good question. It's the kind of question you should always ask. For a lot of applications, it won't make much difference. But the one application that I think is better for a while loop is this one that I gave already. This example here. So let's try writing a statement. So while let's say d sign. Well, I don't want to use the word sign because that's the name of this variable. I can use d sign, I guess. While d sign is d sign divided by sum is greater than or equal to 0.000001. I'll do it that way. 1 millionth. 1 millionth. Okay. Then you can do this. D sign will be equal to the next term in the series. So, actually, you know what? This isn't going to be simple logic. I have to think about this for a minute, how to construct the series so that each time you do it calculates the next term. But the logic of a while, I'm getting long-winded in my answer, so I apologize. So, erase everything I just said. I'm going to start over again. You asked me, for a while and a for, what's better? Okay, the difference, I believe, most of the time you can use either one, it doesn't matter. But when it does matter, the difference is the for statement puts this logic right in the middle, and it automatically specifies the update on the end of it, and the update has to go with this variable. A while statement, the only thing that it checks is the logic. So you can decide what other things you want to change in the middle of the in the middle of the program that follows the for statement. So the for statement has as its basis one variable. Right? You give a name here for x, and it starts at, you can put whatever initial value you want. You can put whatever logic you want. You can put whatever dx you want. Right? This is the basic structure of the for statement. But it fixes what thing it is that you're going to be changing each time through. It has to be this thing. And it has to change by this amount. But for while, you just put while, and now you have logic. And inside of here, you can make whatever change you want. It doesn't have to be just x. And the way that it changes doesn't have to be the same thing every time. Here, the thing that changes is always x, and it always changes by the same amount. Here, change whatever you want. As long as this logic is true, it continues to do it. And then the do while, you put the logic down here at the end. What's better about this? Nothing. Right? Yeah. We might as well have the logic at the beginning. I don't think it really matters.
So for the for statement, the inside and outside.
What's the difference between which inside? You mean these two? Oh, those two down here? Yeah, you mean on this one compared to the last? I'm sorry. Okay, you can put it on the same line if you have a single statement. So on the for, there's the end of the for statement. Now, assuming it's true, it's going to do this, whatever you put next if you want. So here he put y is equal to x plus y. But if you need to have more than one statement, then you need this. And then you can put as much as you want. It's a syntax difference depending on how many things you want to execute while this is true. You know, one thing about programming, it's the same in every language. I listed a bunch of languages there. I'm not an expert at all of them, but I played around with most of them. The syntax is different. You know, when you write for, when you write while, where you put the brackets, and you have to have the syntax correct with whatever program you're using, whatever logic or whatever compiler you're using. But the logic, what's interesting about these languages is they all have the same basic logic. And they all use things like while, for, do, if. They are totally dependent on this idea of these tests, right? Some kind of test that you put inside of a Boolean type of statement that makes a decision about whether to go this way or go that way. Do I do these commands next, or do I skip below the else and do those commands? Without that logic, without that ability to go to different places under different circumstances, these programs would have almost no value. It's that logic that replaces human thinking. That gets you out of the loop, as we say. That's where that comes from, right? You've probably heard that expression. Have you ever heard of out of the loop? That's the whole idea. Get out of the loop. Let the computer do all the work. Get the human out of the loop. If you have to always make a decision about what it does next, what good is the program? You want the program to be as automatic as possible. That's the whole idea. And you know, some of you've probably heard of AI, right? Artificial intelligence. You never heard of this? Artificial intelligence. Okay, this logic, this ability to do these logic tests, is the whole basis of artificial intelligence. So let me give you an example. Let's say you don't feel very well. So you go to see the doctor. What's the first question the doctor asks? Yeah, maybe he says, what hurts, right? Your foot, your knee, your head, your elbow, your stomach, whatever, right? You tell him what hurts. Okay, so what's going on inside of his brain? He has a big chart. You know, what hurts? This is inside of his brain. If it's your leg, he does one thing. Then he asks you another question, right? If it's your head, if it's your stomach, whatever it is, maybe he has 10 or 15 different things that he asks you, right? So let's say the answer is my stomach. Are you vomiting? Yes or no? Did you have diarrhea? Yes or no? Did you eat too much? Did you skip a meal? Did you not eat? Did you eat something spicy? Did you eat some fruit? Did you eat some meat? Right? All these questions. He's running through a logical process of elimination. Right? And when it's all done, supposedly, he's taking 1,000 different illnesses that you could start with. You could be sick 1,000 different ways. And in theory, he's slowly using logic to eliminate them all, so that now he comes down to one thing. I think you have whatever he thinks you have. Okay? And then he has in his head, or maybe he studied it in school or something like that, but he has different kinds of treatments, you know, maybe depending on your age, maybe depending on whether you're male or female, maybe depending on who knows what. You know, if you're taking other medicines already, some medicines can't be taken at the same time, it's too dangerous. So that would eliminate some. So first, there's a whole lot of logic that he uses to decide what he thinks is wrong with you. Then there's some logic for him to decide what he thinks you should do about it. Well, all of that could be programming. Lots of people have done this. This is getting more and more common. Right? The doctors, of course, hate it, because doctors like to think that they're really smart. But the fact is that you could put all of what we know about human medicine in a bunch of logic statements, and you sit in front of a computer, you can already do this. Go on and Google. I have a bad stomach. Did you eat some meat? No. Did you eat some fruit? Yes. Okay, the logic goes this way. Did you eat citrus fruit? No. Did you eat watermelon? No. Did you eat grapes? Yes. Okay, go this way. Were the grapes red or white? They were red. Go this way. I mean, it can all be put in there in a lot of different if statements. Right? That's exactly what we're trying to do. Get the human out of the loop. Get the human out of the loop. Okay. You know, I work mostly in aerospace applications, especially automatic flight control systems. So it makes the passengers on an airplane feel safer when they look in the front of the airplane and there's a human being sitting there and he looks like he's controlling the plane. Actually, it's kind of like a big video game. There are a bunch of computers behind the cockpit, and when the guy holds the steering wheel of the airplane, the stick, they call it, and he does this or that or the other thing and pushes it forward, the only thing that happens is it gets encoded like the joystick of a video game. So the computer says, oh, I see, the pilot wants the plane to go up. The pilot isn't changing anything except telling the plane, I want you to go up. The plane does all the calculations. When the plane goes up, nice and smooth, right? The pilot does this. The computer says, oh, okay, the pilot wants to turn right. Okay, so it makes some calculations. The wings go like that, the tail goes like that, plane turns right. Okay, but it's all automatic. Now, there are some really good pilots around that can actually fly planes very well, but there are not so many of them, because there are so many things that you have to control at the same time. It's not easy. But on the other hand, it is easy to tell the plane, I want you to do this, and all you got to do is turn the stick. That's simple. How many of you have played Wii? Wii, yeah, the video game like Wii. You ever watch somebody play Wii? You can do tennis, for instance. Yeah, it looks so easy, man. I can get out there, I can beat Rafael Nadal. It's nothing like playing real tennis. When I swing that racket, I'm not hitting a tennis ball. I'm putting an input into a computer that calculates something that looks like what would have happened to the ball if I really hit it. That's just a whole bunch of these logic statements. How fast is his arm moving? How high is he above the ground? Is he up high? Is he down low? You know, is he spinning his wrist? So the computer is just trying to use a bunch of logic to say what would happen in the real world if we really did this thing. That's what we're doing. We're using a bunch of logic to replace ourselves. So it sounds kind of crazy. Do we really want to replace ourselves? Don't we all want to keep working? We all want to make a nice salary? What if we're great programmers and we write such a brilliant programming code that they don't need us anymore because it does everything that we can do? It doesn't sound like a good idea. Luckily, it's never happened in the history of the world. No matter how good the program is, somebody can always think of one more thing that it would be nice if this program did. So, you know, back in the old days, when I was your age, if I wanted to make a phone call, you know, I picked up the phone and I had to tell somebody who I wanted to call, and they had to make a manual connection. They had to literally get the two wires together so I could talk to them. And from that point, phones have gotten better and better and better. The bottom line is, it's still the same thing. I talk on this end, somebody hears me on the other end, and they talk, I hear them. It's really wonderful. That part didn't change for 100 years. But now, instead of having somebody sitting in a room putting wires together, now I can use my mobile phone. It bounces off a satellite somewhere. You know, I could call somebody on the other side of the world if I want. I could be anywhere that I want to be. All right, it's amazing how the technology of making that connection, the logic, is improved. So, all right. Sorry, long-winded. You know this expression, long-winded? Long-winded. It's a problem for a lot of professors, definitely for me. Long-winded is when you can't give a short answer. You have to keep going and going and going. Okay. So the use of for loops, for loops are really useful for repetitive calculations. So you can make tables like this. So I think we talked about this early on. You know, if you had to calculate the sign, you could have a loop inside. You could have a while loop that actually calculates the sign from one value of y, and on the outside of it, you could have a for loop. And it starts at y equals 0, and it goes, let's say, until y is less than, or for as long as y is less than or equal to pi divided by 2. And maybe it goes by y is equal to y plus 0.1. So there's two loops. This is the outside loop. This builds the sine table for y between 0 and pi over 2, so 90 degrees, right, by 0.1 radians. And inside of that loop, there's another loop that calculates this series. Right? And that loop has a different logic so that it knows when it can stop on one series. Okay, I'm done with this value of y, this conversion. Now I can move on to the next value of y because of this loop. So 4 is really good if you know in advance how many samples you want to take and what the spacing should be. And the spacing should be the same in between them. Right? Like this one. So I know I want to go from 0 to pi over 2, and I know I want to go by 0.1. That's a good statement. While, in my opinion, while is a better loop to use if you're not sure in advance how many terms you really should calculate. So you want to have some variable logic. Good stuff. Okay. There's CO2, carbon dioxide, right? This is the major greenhouse gas, the most important one. Do you know this word? This word is very common these days in the discussion of climate change. Anthropogenic means something people cause. Non-anthropogenic, something people didn't cause. So fires, biodegradation, animals, actually volcanoes. Volcanoes are a very big source of carbon dioxide. For humans, power plants, cars, fires. Half-life is the time to reduce the carbon dioxide concentration by half if there were no sources. Okay? So this is a good example of while logic, in my opinion, but he's going to do it with for logic. All right, so this is it's a first order differential equation, right? This is a very common thing in nature. You've got, let me pause for a minute. If this is the differential equation, what's the solution, the form of the solution? Okay, well, in general, the solution of a first order differential equation is what kind of function? Exponential. Okay, so if the constant is negative, then the solution always looks something like this. So what we're trying to calculate here is the rate of decrease of carbon dioxide. It's proportional to the amount in the atmosphere. That's exactly what this says, right? So here's the amount. And this would be time. When there's a lot of CO2, the rate of decrease, which is the slope of this line, is very steep. And as there becomes less and less CO2, the slope is less and less. So the rate is becoming less sharp. So that's what this equation says. And like I said, that's everywhere in nature. This kind of behavior is all over the place in nature. So multiply by dt and divide by the concentration of CO2. Before I do that, just to back up for a minute, we know the solution of this equation in closed form. We can calculate the actual mathematical expression for this equation in closed form, thanks to what part of calculus lets us solve this? Well, I'm sorry, I just said the answer. I was going to say what part of mathematics. So calculus lets us do this. And calculus was invented by Newton, Isaac Newton. And there was another guy at the same time. Newton was in Britain. There was a guy in Germany named Leibniz. Okay, so both of these guys invented calculus at the same time. Neither one knew that the other one was doing it. And they got the same answer, which is always a good thing. If they invented it at the same time, we got different answers. Okay, so very interesting. Just one more aside I'll mention to you. I was a guest, and sort of like I'm a guest here now, staying in your guest house. I was a guest at University of Hanover, Germany. And that was in 1994. Not that you care about that. You weren't even born then. But I was a professor in Leibniz, and I'm sorry, in Hanover, and their guest house is Leibniz's old house. So that was pretty exciting for me. I got to live in his house. Okay. So here's the math solution. Equations 1, 2, 3, 4, and 5. Let's go to the next page. And finally, he gets to the solution, which we just said we knew. It's an exponent. It's got a negative value. That's why it's this way. And there's the solution. Okay. So we're gonna program this solution. And he's going to use a for loop. So what he's going to do is start at value t0, right? And if you put t equal to 0 in there, then this is 1. So that will be the initial value of carbon dioxide. And then he'll just make up the delta t and see if you get a nice smooth line. Okay, now I like to calculate the delta, whenever I do these, and I do these a lot, I like to calculate the delta t using some logic. What's good logic for this? Here's the idea. Let me just mention so that you understand. I'm going to plot this over some time. Now, I think that once it does this, you know where it's going. It's actually not very interesting anymore. So it's good to know a time, say, out about here. That's long enough. And from here to here, how many points should I use in order to make this line look nice and smooth when I plot it? Because when the computer plots the points, it'll only plot the individual pieces that we calculate. It doesn't actually know the curve. So it's going to calculate this expression right here. You put in a value of t, and it's going to calculate what c is. That's just one point. It's not going to solve the math. It's going to just make this calculation. So that's the background. So now you have to choose, how are you going to figure out what t sub f is? What's a good number to use? Have you ever heard of settling time? As I said, this kind of behavior, this kind of exponential behavior, this shows up all over nature. So this is very common, right? And a good way of measuring when it's reached a reasonable finish is something called settling time. It's based on the following. E to the minus 1 is equal to 0.37 approximately. So e to the minus 2, that would be approximately 0.37 squared. And if you go down to e to the minus 4, this is approximately 0.02. So back over here, if this is my initial value, this value down here that it settles to will be 0.98 of the total settlement when the exponent is equal to minus 4. All right, so the amount of time it takes for the exponent equals minus 4, that's called the settling time. That's a good time to stop, because from that point on, it's not going to change very much. So inside of here, we have e to the minus kt. So e to the minus kt, I want that to equal to e to the minus 4, and solve for that value of t. And that would be the t where it gets nice and smooth. So that t is equal to 4 divided by 2. All right. So instead of knowing in advance how long I want to make my plot, I can add this to the logic. Once I calculate the solution, I can then calculate how much time I want to see of the solution. Because if I go much longer, it's not only is it not very interesting because it doesn't change anymore, but also if you make a plot, the plot is going to have a fixed width on the computer, whatever it is, 10 centimeters. And the longer you make this tail, the more this gets cramped up so you can't really see anything. If you make it too long, the plot ends up looking like this. Instead of having a nice curve like that, it just looks like this. That's if you have too much of a tail. Okay. Okay, so here's the program. I think rather than going through line by line, I'll just highlight a couple of things because this is something you can run on your own. his for statement, this is the key logic. Starting at time equal to 0, going until time is less than or equal to, and I think that's 50. Yeah, and using increments of 5. So he's only going to calculate the solution at 10 points. If you plot that, only 10 points, you would see straight lines. Instead of looking like a smooth curve, it would look like 10 straight lines put together. It's probably still fine, but if you want it to look smoother, you could take that 5 and make it smaller, say 2, right? 1. If you made this 1, then it would have 5 times as many points. Okay, he goes 80 years. Let's see. Now see here he says you have to enter the half-life. And that means instead of calculating the settling time, you just put it in. Okay. I think we're about done with this one, yeah. And some more examples of practice. Okay? All right, let's go on to 2.8. Any questions about this?
We can choose whatever you want. And when you choose that to 0.88, you choose
Yeah, you could put a different constant in, right? That solution depends on the value of k. So this value of k, that was some kind of physical concept that we got from physics of that equation, an atmospheric constant or something like that. So if you calculated inside of the program the settling time, you could then put in any value of k, because maybe it's different in certain different locations, and just run the program, and you wouldn't have to keep changing the amount of time that you would look at the half-life. So he said, let's look at 80 years. Maybe you want to look at 50 years, or 30, or 20, or whatever. Actually, I think it's not so much the amount of time to look at as it is what is a reasonable amount of time to see everything that's going to happen. A reasonable amount of time to see everything that's going to happen is 7 years. Because after that, it doesn't really change. But before that, it changes a lot. You don't want to cut it off too soon or replace something. But if you keep going too long, it's a waste because it's only going to, it doesn't add any new information and it makes this more and more time. Does that answer your question? Okay. Yeah, 2.8. Any questions? Okay, let's just go ahead and by the way, everything will be shared for everything. Is that it's not working? Okay, so let's all try to quiet down a little bit, okay? Please. Okay, so this is on the formatted output. You can get fancier on the output. You can change the type of number printed. By the way, let me ask you, in BND, I have 500 bill. There's some coins, right? Yeah, the coins, the metal, and they go down to 100 or 50, or what's the smallest? 200? Yeah, so if you were going to write a program that printed money in BND, the last digit only has to be 200. Right? You don't really need anything beyond that. So for instance, you could use integer for BND. Right? Because 200 BND, there's no fraction of a BND. Now, if you're writing one in US dollars, as I said the other day, the smallest thing in our money, the smallest is 1/100th of a dollar. So you need 2 decimal points. So that's a good example, comparing those two, of when you would want to have control what kind of number is printed and how many decimal points. Okay, guys, if you want to talk, right, you know the rule. In here, quiet. If you want to talk, go outside. It's okay with me? Just don't stay in here and talk. That's the one thing that's not okay. All right. So you can print a table, and for the U.S. dollars, okay. Please. Yeah, I just asked you to be quiet. I'm sorry that you can't respect that, but I have to ask you to leave the room now. Okay, so you can print, if you're printing a conversion, so you have sales in dong, let's say, and next to it sales in dollars. On the dollar side, you can put 2 decimal points, but on the dong side, you can use an integer. You wouldn't put a decimal point. If you put a decimal point, it wouldn't really look right. But the same thing on the dollars, it wouldn't look right if it has extra decimal points. We haven't done complex numbers yet, but you've had some mathematics with complex numbers. Integer and real, imaginary part and real part. Complex numbers are really important in dynamics. Did you do them at all with Andy? Okay. Well, in the higher dynamics, almost all the calculations are done using complex numbers. So if you're printing complex numbers, it's really nice to control the output because a complex number is really like 2 numbers. And you want to make sure you understand which part is real and which part is the imaginary. Or sometimes, as you know, a complex number is written as a magnitude and then a phase angle. Right? But either way, it's 2 different numbers, and you want to make sure that you can separate the notions. Justification of output. What's justification? It's one of those English words, there's so many that have multiple meanings. So what's the meaning of justification? In general, when somebody says justification, they want a valid reason why you should do something. Yeah. Like, you have to take higher level language. Really? What's the justification? So you're asking for a valid reason. The justification is that all engineers need to know how to do this logic. But in this case, it's talking about output. In output, there are 3 kinds of justification. So if this is a page, if you print everything so that it begins on the left edge in a nice straight line, that's called left justification. If you print everything so that it ends at the end of the right line, so it ends over here, that's called right justification. So left justification, let's say I made a list of our names. We have names that are different lengths, right? 2 letters, 3 letters, 10 letters, whatever it is. If we did it left justified, then the right edge would be dragging because everybody's name is different, but it would begin in the same place. If we did it right justified, the right edge would be straight and this edge would be jagged. So the beginning of our name would be in a different place. Here, the end of our name would be in a different place. Okay? Then there's a 3rd kind of justification that's called centered. All right. Here's my last. Centered. And centered starts in the very beginning of the screen or page, and then whatever it's writing, it spreads out only as far as it has to write that amount. Okay, so here our names would be jagged on the left and jagged on the right. Except it should be symmetric about the center. So if you have a long name, your name would look like this. If you have a short name, it would look like this. In both cases, they would have the same center. Okay? So there's 3 different kinds of justification. Exactly the same thing in Excel. We're going to do Microsoft Excel next. And when you do the cell formatting in Microsoft Excel, you have to tell each cell whether you want it right, left, or center. It makes a big difference in how beautiful it appears on the page. It's common with money, for instance, to use right justification. So if you're adding, let's say, B and D, you might have 5,000 and then 10,000 written like that. We're used to having a right justification that makes it easy to add the numbers. You can see how they add. If you use left justification, that doesn't really look right for adding. Your eye might be fooled into thinking this is 6,000 instead of 15,000. This is very easy because the columns that go with each other are lined up. So something like money, you want to always use right justification. But for some things, left justification makes more sense. Maybe you're going to make a list of countries. United States, Timbuktu. This probably looks better if they all start in the same column. And then over here, you can put the money. You have the money end on the same. Okay. So that's justification. Yeah. Okay, here's some different examples. I'll just show you these. These numbers could be, do you think this column is right justified, left justified, or center?
Right.
This one right here. Actually, you can't tell, because if they're all one digit, it'll look exactly the same, whether it's right, left, or center. How about this one? Right justified. Okay. And how about this one? You can't tell. All right, so this is an example of integer. If you ask it to print an integer, there's no, oops, oh, those are just blanks. If you ask it to print an integer, there's no decimal point. This is an example of printing a number with a fixed number of decimal points. Right, so you say 3 decimal points for every number, no matter how big it is. This is 7, 18, 122, but in each case, there's 3 to the right of the decimal point. And that other one, oops, for a second. This is an example of printing it in, I think what's called floating point format. So in this one, you always have the same number of significant figures, same number of significant figures, and then the exponent tells you where to put the decimal point. So when it says 1.91 e to the minus 002, if we printed this number using this format, what would it look like? If I print this number using this format, 3 decimal places, it would look like 0.019, right? It wouldn't print that line. So printing this number in this format, it would look like 0.019. What if I print this number in integer format? What would it look like? 0. It's 0.01. It's not big enough. It has to be more than 0.5 to be printed as 1. So in integer format, it would put 0. How about this number? What if I print this number in this format? What would it look like? 6540.000. That's what it would look like. How do I know that? Because 10 to the 3, so it goes over 1, 2, 3, 6540. And we told it to put 3 digits to the right of the decimal point, so 0.000. How about this number in this format? I gave you again, I started at 0 point. All right, 10 to the 4, 1, 2, 3, 4. So 3 zeros and a 9. But we're only going to print 3. And it should be 0009. That's a 9. It gets rounded up. So it would look like 001. That's what it would look like. And what if you print that number in this format, in integer format? 0. How about this number in integer format? 6540. No decimal point. Just 6540. Okay? So you can see choosing the correct format is really important, because especially the most dangerous thing is to not use this format. This format will always preserve the number of significant figures, and it moves the decimal point by using the exponent. But if you print this number in this format, right, and you lose the 1 out here, if you print it as an integer, it looks like 0. So you lose completely what that number is. Okay, let's So the next slide. This is the example of printing a table. Okay. So this is using a C output command, and he just put a bunch of blanks in there. I think it shows his periods, but they're blanks just to make spaces. So IO manip, that's input, output, manipulation. What's manipulation? Manipulation is a good English verb. It's a verb. When you manipulate something, what do you do? Yeah, it's sort of like a puppet show, and you're in charge. You're pulling the strings to make everything move exactly the way you want it to move. That's manipulation. It's common. It's a common thing in a relationship between boys and girls. That somebody thinks they're being manipulated. The other side is doing something. They're pulling the strings and making them do something they don't really want to do. Okay, so in here, what we're manipulating is the output of the computer program. So we get the A where we want it, the B where we want it. We get the number and the format we want, located where we want it. Okay. You can go back, you can see there's some new commands in here. You can look them up, and you can see the syntax. I think I won't spend too much time on that. Scientific notation, that's the one with the exponent. Right? Set precision, this tells it how many decimal points, and so on. See, set number of decimal places to display. Set the width of the output, 10. Changes the display to scientific, and so on. So you can see what these things are. Yeah, right justification. Here's the four main input-output commands you should know. Okay, what do you think is the difference between non-persistent and persistent? Who knows what persistent means? Persistent. That's somebody who just never gives up. Just keep, yeah. Non-persistent means that. Okay, so when you use this command, it's non-persistent. So it sets the width of the print space, but you can come back and change it later. You can use it differently for a different area. These three are persistent. Once you put a persistent function in, it stays that way. Okay? Okay. Here's a demonstration of persistence. All right, so set width is non-persistent. Okay, so the set width tells the display how wide to make the space that you're about to print into. So you can decide, for instance, if you want to use this kind of display, 3 decimal points. You have to set a width on the page that will get printed into, and then you have to tell it how to justify it. All right, so let me go back. Let's look at this example again for a minute. Let's say that we set width for B and D. We set the width equal to 8. So that means there are 8 columns available. If we print something that's got 4 digits, like 5,000, and it's right justified, it'll look like 4 blank spaces with 5,000. If it's left justified, it'll look like 5,000 followed by 4 blank spaces. And if it's centered, it would be 2 blank spaces, 5,000, 2 blank spaces. Okay? If I want to print 100 million B and D, and I have set width equal to 8, I'm going to screw up. Right? You can't do it. Because 100 million takes 9 digits. And I told it, you only get to use 8. Okay, so what do you think it does?
It's really late.
To tell you the truth, I'm not sure what it does. It might just print garbage. something that doesn't have any meaning, or it might tell you this is an error. You might get an error in compilation, a syntax error. When you set width, you have to take into account every digit that's going to print. So if you're using scientific notation, if you're using this kind of notation, what's the minimum width you would need for this? 1, 2, 3, 4, 5, 6, 7, 8. You need at least 8. Right? Now the beauty of this is, it doesn't matter how big or small the number is. Every number can be printed in this form with 8 spaces. If it's 100 million, what would it look like? It's 10 right? Right. No, it is too big. It should be an 8. Sorry. Yeah. So happy. I'm so happy. Anyway, so here's two numbers that are hugely different in size, right? This is 100 million and this is 1/1000, roughly. And they can print in exactly the same way. So that's the nice thing about using this scientific notation. Then you could set this, let's say, set width for these numbers at something like 12, and then you could have the center. So these will print in a nice column. It's 8 wide. If you told it you had 12 spaces to work with, center it. So it would put space, space, these 8, space, space. Space, space, these 8, space, space. It would be a nice, regular appearance. Okay.
What exactly is elastic?
If it's set, yeah. If the centering, you tell it to set width. Is that what you're asking? What if we make this 11? Right? And there's 8 of these, so there's only 3 blanks. How does it center? Yeah, I'm sure that it has a default, right? Of putting either 1 in the front, 2 in the back, or 2 in the front, 1 in the back. I don't know which one it is. But whichever one it is, it would do the same thing every time. Actually, this is a great word. Did we use this word yet? This is a really important word in computers. What does it mean, default? Default means what it's going to do unless you change it, explicitly change it. There's sometimes this is added to this as the word settings. Default settings, okay? So when you buy your laptop, you take it home, you turn it on, it starts up the first time. You've got a nice screen to look at. It's got, I don't know, maybe the background is a picture of Windows XP, something, whatever it is. Okay, what's one of the first things that you override? Override is the verb when you do something other than the default. So maybe you get a picture of your girlfriend and you put her in the background, so instead of seeing Windows, you see your girlfriend, right? That would be an example of going over the default and changing it so that it's what you want it to look like. Maybe it comes with a default setting that says, if you don't touch it for 2 minutes, it turns itself off to save the battery. This is really annoying because sometimes you get up and you leave for 2 minutes and come back to the computer turned off. So you decide, I want to give myself a little more time. So you change it from 2 minutes to 5 minutes or 10 minutes, right? So you've overridden the default. So computers, all the computer compilers are full of defaults. The default is what happens if you don't change it. And back to your question. So what would happen here? If you had a width of 11 and you told it to print 8 digits, that doesn't divide evenly left and right. So how can it do a center? I don't know the answer, but there is a default in the computer that would put it either 1 on the left and 2 on the right or the other way around. And how would you get past that default? Let's say the default is 1 space on the left and 2 on the right. And what you really wanted was 2 spaces on the left and 1 on the right. What would you do? There's a bunch of things you could do, but one simple thing to do would be you could print a character variable blank first, and change the width to 10. If you change the width to 10, then it's going to be one on the left and one on the right. And if you print first a blank space, then you'll end up with two on the left and one on the right. So that would be an example of something you could do really fun. Okay. Look at all those data output commands. Now, so I highly encourage you to go through line by line and make sure that you understand what's going to happen. Then run it. And make sure that what happens is what you thought was going to happen. If you have any questions about these, please ask them. If you're not sure what these commands are going to do, but I think you'll figure it out. I don't think it's that hard. It's always a little bit confusing the first time, but you'll get good at it. Okay. Do the next slide. These are a few more commands. I think they're self-explanatory, but you can ask me if you're not sure what they mean. But for instance, you can decide whether or not you want a positive sign on a positive number. A negative number will always have a minus sign in front. And by the way, if you're doing set width, you want to be sure that you make space for a negative sign. But a positive number, it's up to you whether you want it to print a positive or just leave it out. Right. When we write numbers, we don't usually bother to write plus. If I write 5,000, you know that means positive 5,000 unless I put the minus in front. Then it means minus 5,000. But when you're printing, if you want, you can print some plus and some minus. This shows you this decimal point business, so you can use that with the ND, for instance. So if you have a number that has a fraction, so there is something non-zero to the right of the decimal point, it prints the decimal point. But if it's an integer number, if it's a whole number, it doesn't even bother to print the decimal point. That's what this can do. But these are relatively minor. So here are the examples. Yeah, go ahead and run them to practice. And again, what I suggest you do is, before you run the file, look at each line and figure out what it's telling the computer to do. Then run that line and make sure it's what you thought it was. Trigonometry, power series, sine series, more trigonometry. Okay, let's look at 2.9. Now 2.9 is completely different. We talked about this a little bit last time. 2.9 is single result functions. So something like sine. This is where you get to make up the function that you want. Okay. There are library functions. They already exist. They're in the library somewhere. And in CMath, right, functions like square root, cosine, power, those are all built in. Because people use those a lot, so you shouldn't have to write it yourself. And here's some single result functions set with. Single result means the function calculates exactly one thing, it does one thing. Set precision. Okay, user-defined function. Single result function returns one result. An avoid function can return one or more results. Okay, so we're going to look at single result functions. Okay, this is good terminology. Okay, you know the rule. Please. All right. So this is the terminology of a single result function. In a single result function, you give the function what are called arguments. What is an argument usually? Yeah, it's like a debate. It's like we disagree with each other or something. So my argument is what I believe, what I think the right position is. So I tell the function what the arguments are. Then the function calculates something and it sends back its response. So the function result is one value, and it either gets sent back assigned to a variable, or it gets printed directly as output, depending on what kind of function it is. So if I write this, z equals sine of y, what's the argument?
Sine y. That's y.
The argument is y, right? What's the function? Sine. Okay, and what's the single result? Z. Right? Okay. When you write a function, when you use a function, the general word that we use is to say we call it. You call the function. So for a void function, you call the function without assigning it to a variable. You can have arguments, but you don't have to have arguments in a void function. When you call them, you call these functions, it does a single, performs some operation, like a calculation, or maybe it writes output. A void function does not return a value. Okay? That's the key difference between these two. It can return information by changing the values of the arguments. Right? So this is dangerous. But let me just mention this now, because this is something that's driven me crazy in my career. You get the benefit of my wisdom, or my lack of wisdom. All right, let's say I have this function, like maybe I'll make a new function, Joe. So I'm going to make up this function, Joe. All right, so over somewhere I define the function. Function Joe of y. All right, so maybe my function is that I want Joe to be equal to y squared plus 2 times y. Maybe that's my function, simple function. Right? There's a return statement down here that says to go back. So in my program, when I have z is equal to Joe of y, it transfers control over here. It calculates what Joe is, and it returns back. And now Joe becomes the value, z becomes that value of Joe. That's the idea. Now here's the danger on this thing. On these void functions, you can return information by changing the value of the argument. So in that case, over here somewhere we have an argument. The argument here is y. So let's say I do y equals y plus 1 and return. If I put up here y equals 3, and now down here I put c out with y, what value is y at this point? 4, right? Because it was 3 when it went into here, and it got changed to 4 and it came back, and now it's got a new value. So this function not only changed Joe, it also changed y. Okay? Well, if I put this in as a variable, that's not so dangerous. Well, what if instead of doing y equals 3, I just did this? Okay, now over in the function, it receives Joe, and it receives right here 3. So everything that looks like y in here is marked over here with this symbol 3. So when I do this command inside the function, it changes 3 into 4. So now if I come over here and I say C output 3, well not that, that's a character. C output 3, what will it write? 4. Yeah, I changed 3 to 4. I really screwed it up. But forget about C output. Let's say I put P is equal to 3 plus 3. What's the answer? 8. Right? The answer becomes 8 because by passing 3, by putting 3 as my argument, and having this statement inside the function, this statement takes whatever shows up right there and it turns it into itself plus 1. So if the thing that shows up there, the argument, was originally 3, now 3 is 4. So 3 plus 3 is now 8. And I can tell you the rest of this program is going to be garbage. So that's going to be really a problem. I've done this before. This is one of those times where you just you beat your head on the wall trying to figure out what the hell is going on. How come this computer doesn't know 3 from 4? What is wrong with this computer? There's something wrong with the computer. I'm sure there's something wrong with the computer. It can't be me. There's something wrong with this damn computer. I wrote 3 plus 3 and it thinks the answer is 8. What kind of a loser computer is this? Okay, yeah. Question? Yeah. So what's the takeaway message from this? When you define functions, when you define a function and you call a function, I highly recommend that you always call it using a variable name, not a number. Just in case you do something like this, which I've done many times, something stupid like that. At least if you put y in here, you didn't change the value of 3. You changed the value of y. 3 is still 3. Okay, that's what this says. That's this one right here. This is a very dangerous statement. It should be bigger. So, changing the values of the arguments, that value gets transferred back to the main program when it goes back. Okay. The best way to create a function is to place a function declaration. Right, that's a comment. So this is just telling you this is what it looks like. So you're going to have a type of function name, and then as many arguments as you need. So you get to make up the function name. And then inside of the main program, you'll call that function. Now, here's the main program. These are the only kind we've had so far, these main programs. So inside of the 2 loops, this is the whole main program. This is like a separate program. That's the function part over there. So it begins with the function, it's got all the commands inside of the function statements, and it ends with the return statement. Every time the function name appears up here, it transfers control down here, does this, and then goes right back to that spot and continues. So this could be inside of a do loop. Like I gave you an example a little while ago with the while statement, where we're going to calculate the sign at 0.1 radian intervals, all the way from 0 to pi over 2. Inside of that loop, we call the sine function 15 times. Every time we call the sine function, it goes into the function sine, and it calculates that series that converges on the sine. And when it's done, it goes back. And then it finishes that loop and comes back again, and it has a new value of radians. And then it says, what's the sine of this value? It goes to calculate it again. Okay? So, depending on how many for loops, do loops, if statements, and so on, depending on the branching and what kind of a function it is, you might call the same function millions of times in a single program. Right? Something like the sine or something like the power. Maybe you use the power function over and over again in every loop. Okay. Okay, so what is this function doing? Here's an example. He gave a function named poly1. And down here, the function is defined. And what is the polynomial? So this is calculating the same polynomial every time through. That polynomial is 3.2 times y cubed minus 2.3 times y squared minus 4.1 times y plus 1.3. 4.1y plus 1.3. Okay? One other piece of syntax I'll show you is inside of the program when you're doing the calculation, You'll have left-hand assignment statements, just like you do in any other calculation. Somewhere in there, you pick the one that is the value that you want to actually return. And that goes on the return statement. So for instance, if I put return Joe, then wherever I calculated Joe, that's the thing that goes back. He used A and S for the answer. That's the thing that goes back, the answer. That goes back into that location. Because that's the function name. So when we call the function, we call it by that name. But the value that gets assigned to it comes from this right here. And we can have anywhere we want to assign. Okay. Yeah, this is a good example. I think you can, I think this is one you can read on your own. It's exactly the same format and style, right? What's different is that this one's got 5 different arguments. And it's a longer polynomial, 5 arguments. Here's 2 functions as part of the same structure. Okay? And there's no limit as to how many functions you can have. So here's the main program, int main. It's got the 2 brackets. Everything inside of there is the main program. Then there's a function named, I can't read those. A function named doctor, and another function named range. I think that says doctor. Can you tell? Doctor, yeah. So here's doctor and here's range, and they both have the same basic structure. Here's the beginning of the function, and then whatever it does, and it ends with a return statement and the right bracket. And then here's the next one. It begins with the left bracket, ends with the right bracket as a return at the end. This one is an integer function. This is a character function. You could have double precision functions. You could have float functions. And yeah, let's pause for a minute. So the main program here calls doctor, right? That transfers control into doctor. Inside of doctor, it calls range. That transfers control to range. Now range makes its calculation. That value gets returned back to where range was called. So it's still inside doctor. This finishes its calculation, then that returns control back to where it got called, doctor. Then the next thing that happens is this line. Okay? Yes? The difference between return 0 and return these answers? The functions have to return an answer to whatever called them. The main program, when you get to return, it's done. Return 0 is just, it's always the last statement of the main program. Okay. Go ahead, Alex. Okay. Okay, so here's some, oops, back up for a minute. Here's single result functions using series solutions. So this is exactly what I talked about a few times already. So the first one is the sine of an angle using a power series. Then you've got exponent using a power series. can look at the line-by-line code, but I just want to point out, I've talked a lot about calculating the sine series. So here it is again, and he's got it programmed. The example shows the sine series program. You can also see other kinds of power series that are supposed to converge, like this one. You know, this is the exponent. Exponents are particularly tricky series to converge. I want to point something out. Inside the numerator, every time it gets bigger by whatever value of x is multiplied. So here's x squared, then x cubed, x to the fourth. So if you take the exponent of a big number, these numerators grow really fast. The denominator, from 2 factorial to 3 factorial, the denominator gets bigger by a factor of 3. Right? It goes from 2 to 6. But if the numerator is, let's say, 100, the numerator gets bigger by a factor of 100. So the next term in that series is much bigger. Then you go to the next one, from 3 to 4. The numerator gets bigger by another factor of 100 times bigger. The denominator gets bigger by 4. So you have to go off a long way on the series before finally the numerator starts getting bigger faster than the denominator finally starts to get bigger faster than the numerator. And so finally this fraction starts to get smaller again. But for a long time, every one of these terms is bigger than the one before. So it takes a really long time for that series to converge, if that's a big number. But if x is a really small number, right, the bottom gets bigger from here to here, from 2 to 6. If x is something like 0.1, this goes from 0.01 to 0.001. Now the numerator gets small really fast, you only need 3 or 4 terms and you're done. So the number of terms in the series it takes, the number of terms in the series it's going to take in order for it to converge varies tremendously depending on what the value of x is. That's why it's so important to be able to know when your series is converging. So here he's writing his own function subroutine to calculate the sine. He can't use the name SIN because that's built into C++. So he's chosen the name SINB. But the idea is to do the same calculation, but to show you exactly how he's doing it. So here's how he does that series approximation. He's using a do-while logic. Remember, I said that I thought do-while was the best logic to use if you're trying to find a converging series, and that's exactly what he's doing. So let's pause for a second, Alex. Can you go backwards for a minute? Oh, sorry. Okay, so here's the series. And this is the logic. Thank you. Okay, so here's the series, and earlier I said it would take me a few minutes to think about how to write the algebraic expression for the next term in the series. So here he's done it, it's very clever. So you can start with an integer of n equal to 1, and so the first term is minus y squared over 4 times 1 times 1 plus 2 times 1. Right? So this is a way of approximating the factorial in the denominator. And then sine of y is equal to the old sine of y, which starts as y, plus that next term. And then you change the difference by 100, and then increase n. And while that difference is greater than 0.000001, go ahead and do it again. So you keep calculating as long as this difference is bigger than this value. So this is not based on a percentage. This is based on a fixed value of difference. Okay? So when will this decide that it finally knows what the sign is? How many significant figures would you see? 5, right? When the difference is no longer bigger than 0.00001, then it quits and goes on. And then it returns the value of sign 1. Okay. So again, you can do this, you can run this program at home. What I would suggest to you, I don't know if you can pause it, Alex, but I would suggest that you take this example at home and put a C output statement in here to calculate the difference. And that way you can watch that series converge. You can see how each term is smaller every time it goes through. And you can see how many terms it takes in that series to get it to converge. Put in a really small number for sign, like 0.01. Put in a big number for sign, like pi over 2. And see how many terms it takes in order for it to converge. Let's go back and just review this list. Okay, benefits of functions, modular, what does that mean? Modular means that the function, like sine, it's its own little piece, all by itself. It's not part of a bigger function. Okay, that ties to the next one, transportable. What does that mean? You can put it in any program you want. Once you write the sine function, for instance, you can then put the sine in any other program you ever need sine. You just add it. Easier to debug. Why would we say it's easier to debug? Because usually it's short. It's designed to calculate one thing. So debugging that one calculation is pretty easy. It's not part of a huge program where you have to debug everything at once. You just have to see if it got that part right by itself. It's easier to read for the same reason. It can be grouped into objects. What does that mean? It means something like a library, right? So like C math, you could put all the trig functions into one group. And then every time you run a program where you need trig functions, you just load that group. Yeah. Okay, let's see the next one. So here are the examples. Exercise 2.9. Okay, let's look at lecture 210. Yeah, how are we doing today? Yeah, there's only 4 more. Okay, let's take a break for just a second. Let's just discuss philosophically where we are in the class. So, remember there are 4 main chunks. There's the C++ chunk. Then there's Microsoft Excel chunk. Then there's numerical methods chunk, which is all math. It's not really programming. And then MATLAB. Okay, so in my opinion, the most important chunk of the 4, well, it's a toss-up between number 3 and number 4. I think MATLAB is the best language to know if you're only going to know one. But C++ is kind of a similar version of MATLAB. So learning C++ along the way is a good thing to do. But I don't really want to spend the whole time just talking about C++. I want to make sure we get to talk about MATLAB. So that's why I'm speeding up a little bit. We can always come back and review questions if you have questions. So that's the first point I want to make. I know we're going fast, but I also know that we can always come back and discuss it. Which is point number 2. You're supposed to look at these lectures and try the exercises yourself outside of class. Make sure you do that so that if you have a question, you can ask it. All right? Because I'm good at a lot of things, but I'm not good at all at reading minds. So I don't know whether you understand it or not. So if you don't understand it, you have to tell me. Okay? We just passed exercise 2.9. Be sure to do that. Now, 2.10 These are functions just like the last time. The logic is exactly the same. The syntax is a little bit different. It's a so-called void function. So you declare and you define it the same way as a single result, right? But it has a different syntax. It starts with the word void. You declare it before the main program, and you can define it after the main program. Void functions do not return a result or a single value. So when you call a void function, it's not like the sign where you say y is equal to something like this. Z is equal to Joe of y, and the function calculates the value of Joe. A void function is more like set width, right? Set width 12. So in that set width command, you're telling the output to put 12 spaces aside so that you can write the number inside of the 12 spaces, or 8, or whatever the number is, right? You set width. But there's no value that comes back to the program. Nothing gets assigned, right? It creates some result, but that result isn't a calculated number like this is. So that's the difference between void and function. Okay. You call the function name as a statement, and you can put arguments inside of it. So just like this set width with 2 parentheses, 8. So you put an argument in there and it becomes a function that uses the argument 8 to do the thing that